Welcome to the webinar EICASLAB Rapid Control Prototyping in PiSA project. This webinar aims at giving an overview of the work carried out within the European PiSA project by focusing on the sub-project 2 and its user case. In details, the topics presented in this webinar will be an introduction on PiSA European project, main role and activities of EICAS in the project, an overview on the sub-project 2 presented in the webinar, a description of the simulation and rapid control prototyping development phases, an user case example, the test scenario taking into consideration, a short movie of a real test performance. So, let us start from a brief description about PiSA project. PiSA is an integrated project of the 6th Framework Program. The idea that leads the project is to combine human flexibility, intelligence, and skills with the advantages of sophisticated technical systems that can help workers without replacing them. In fact, PiSA's main objective is to keep humans in the production loop by supporting them with revolutionary and qualified tools. In order to reach such innovative and productive human-machine cooperation, time-sharing robots and workplace-sharing robots have been investigated and chosen as the solution that best fits the project objective. The term time-sharing robot identifies a system where humans share time with the robot during its work. In time-sharing, humans and robots work at the same task at the same time but performing different operations without any physical contact. Workplace-sharing robot instead means that the human operators share the workplace with the robot for executing the same operation, with or without physical contact. PiSA involves many partners along all the Europe. In particular, we can find 4 industrial companies, 7 small and medium enterprises, and 7 research institutes that cooperate into the project. The main role of EICAS in PiSA project deals with guaranteeing the human safety into the working area. Safety is a critical and important topic when human and robot share in some way the same environment without a physical shield that divides them. So, EICA's goal is to supervise the human presence in the working environment in order to avoid dangerous and hazardous situations during the production cycle. In detail, when we speak about safety in PiSA human-robot cooperation, some functional requirements have to be satisfied. They are: to supervise the area in the operating environment that the robot covers during its task, to allow the cooperation human-machine only when it is foreseen, to signal hazardous situations to the robot controller for stopping the movement, to give the possibility to change dynamically during robot's movements the shape of the supervised area, and to slow down the robot velocity by means of an override factor during the human-robot approaching. Well, as I said before, in the next slides we will focus on time-sharing robots, that is part of the PiSA sub-project 2, called also SP2. SP2 involves a time-sharing robot composed of 2 arms and able to carry out complex assembly tasks. In the following, it will be called dual arms robot. In this case, robot and humans work at the same time but on different operations, without physical contact. The innovative aspect considered in PiSA is to allow the human to approach the robot under certain circumstances, in order to fulfill specific operations such as localization, support on alignment, supervision, task reprogramming, exception handling, and so on. All these operations require knowledge, flexibility, and human skills, so they need to be carried out by a human worker. When we start to think about this approach, it is clear that the safety is a key issue to be addressed. EICAS has answered to such an issue by designing a suitable control of a higher hierarchical level in the following called Safety Manager, able to monitor the human presence in the area and to command necessary actions for guaranteeing the human safety. To design the Safety Manager, EICAS has adopted its control design methodology, implemented through its own professional software suite, EICASLAB. EICASLAB is the professional software suite that supports the developer with several tools in all the control designing phases, from the system concept and like real-time simulation to the rapid control prototyping until the code generation for the final target. In PiSA project development, many EICASLAB tools have been involved, and for example we have used the Sim Builder for modeling the dual arms robot and develop the control strategies, the Sim and the Post for performing simulations and offline analysis, the MPI CPO Manager for parameters identification and optimization during the developing of the tracking algorithm for detecting and foreseeing the human position, the scheduling chart for managing the control activities and their synchronization, the scheduling chart for managing the control activities and their synchronization, the Rapid Control Prototyping Manager for managing the real-time application during the Rapid Control Prototyping test, the external interface configuration for connecting the external subsystem and sensor, and so on. As is schematic presented in this slide, after the simulation, EICASLAB allows to switch the project on the Rapid Control Prototyping modality. To be noticed that the software developed in simulation, represented in figure by the chip, is the same one used in the Rapid Control Prototyping activities. EICASLAB, the RCP module, and all the project software runs on the so-called EICASLAB Rapid Control Prototyping platform. The RCP platform is based on a standard PC provided with suitable interfaces and a real-time kernel support. On the RPC platform, the developers has at disposal a real-time operating system, multi-core and multi-thread management tools, a real-time manager for commanding the real-time layer, the possibility to run a friendly graphical user interface, and the possibility to interface directly the external hardware. For interfaces external devices, EICASLAB offers some built-in libraries, or the access to a pre-organized structure of functions that make easy integrate custom interfaces. In PiSA subproject 2, the hardware to be connected are the laser scanners and the external controllers, the robot controller and the central controller. Hence, as you can see, the Safety Manager is a control system that works on a high hierarchical level. It takes the measurement about the human presence in the area through the two laser scanners, and then it closes a loop on the robot controller by giving the permission of work plus an override factor used for slowing down the robot. For a better understanding, in the following slide, I will show an hypothetical situation that covers the SP2 application. Here we have the dual arms robot station, the Safety Manager, and the first laser scanner. The second laser scanner is positioned at the opposite corner of the table, and so it is not visible in figure. After an offline configuration, the system can be switched on. For the first seconds, the Safety Manager detects and memorizes the contour of the place for making its own references. Then the Safety Manager starts to monitor the first surveillance areas, and each laser scanner sets a protective and a warning area to watch over. Until the humans remain external to the warning areas, the robot works normally, and the safety manager does not interfere. Since the human oversteps the warning area, the safety manager starts to operate and gives to the robot controller an override factor for slowing down the robot. The override factor is proportional to the distance between robot and human. If the operator oversteps also the protective area, the safety manager revokes the permission of work, and the robot controller stops the movement. As soon as the operator comes back, the safety manager restarts to grant the permission of work and to set the appropriate override factor. Now, beyond these basic safety functionalities, one of the requirements is to allow the human to approach the robot under certain circumstances. For this reason, the shape of the supervised area can be dynamically changed according to the application requirements. In this case, a passage in the green protective area has been opened, and the worker can enter to accomplish his job. The robot does not stop, it only slows down according to the human distance. Once completed the operation, the worker steps back, and the areas are closed and protected again. After the simulation and the rapid control prototyping phases, the safety manager is ready for a first real test. A suitable test scenario has been set up by EICAS with the EICASLab RCP platform connected directly to the real interfaces. As you can see, there are the two laser scanners with all the converter and the connectors enclosed into the hardware test box, and a simulator for the robot controllers. The whole environment may be monitored and displayed on the Safety Manager PiSA graphical user interface, where it is possible to follow the system status and the test evolution. On the left, we can see a snapshot taken from the graphical user interface. We have depicted the two laser scanners, the robot, signaled by the red spot, the human operator, the supervised areas, and the room contour, in black color. In this environment, the validation test of the system can be performed. In particular, it is possible to reproduce a collaboration situation by opening a corridor toward the hypothetical robot, to verify the safety signal sent and the override factor for slowing down the robot, to test the response for protective area overcomes, to test the dynamic area change, and to test the failure detection by injection of the faults on the communication channels. And now a short movie will show you the performed trial on the test scenario. Good morning, ladies and gentlemen. Today we are here to show how the Safety Manager system, developed by EICAS Automazione within the European project PiSA, works in a real case. The Safety Manager goal is to supervise the human presence in the working environment, in order to avoid dangerous situations between the human workers and the robot during the production cycle. In particular, the prototype that we will show you today is customized for the SP2 use case, where the time-sharing robot is considered. A representative testing scenario for the Safety Manager has been implemented at EICAS premises, in order to verify and validate the system performance. The laboratory scenario is composed by several components. First, there are two safety laser scanners for monitoring the working area. They are placed at the corners of a rectangular reference, highlighted with black stripes, with an height from the ground of roughly 30–50 cm. Then there are four cables, 5 meters long, that connect the laser scanners with the hardware test box. It contains the power supply, some connectors, the serial converters, and the laser scanner's communication interfaces toward the Rapid Control Prototyping platform, called from now on RCP. The RCP platform is based on a standard PC, provided with a real-time operating system,
in this case Linux RTI, and with a suitable interfaces for the sensors. In this case, we have a serial PCI card and a data acquisition board from National Instruments. On the RCP platform runs the EICASLab software suite, equipped with the Rapid Control Prototyping module. The Safety Manager system, with all blocks and functionalities, has been implemented in EICASLab. Besides, a devoted Safety Manager graphical user interface has been also implemented for monitoring all the safety issues. It receives data from EICASLab suite in order to display in real time the contour of the room, the human personnel that is moving nearby the robot, and all the other information concerning laser scanner status and connections. The testing environment is completed by another PC that emulates the P4C central controller and the EPK robot controller. So, for concluding the introduction, the Safety Manager works at the highest hierarchical level of the control architecture. It takes the measurements about the human presence in the area through the two safety laser scanners, and it gives back the permission of work plus an override factor for slowing down the robot. And now we can start the test. To begin our test, we start with the Safety Manager running in idle state, as you can see from the red light at the top of the screen, and with the human operator standing outside of the supervised area. From the P4C emulator we can activate the Safety Manager protection, and after a few seconds necessary for the calibration, the green LED in the Safety Manager GUI lights up by indicating that the protection is enabled. Always from the P4C emulator we can change the protective areas, and, for example, we can switch from the use case 1 to the use case 2, as shown by the enlargement of the fields set in the Safety Manager graphical user interface. At this point, the operator starts moving in the area toward the first laser scanner. The Safety Manager detects him, and we can follow his movement directly on the graphical user interface. Until the operator remains outside of the warning area, the robot can work normally, but as soon as he oversteps the warning area, an override factor lower than 100% is sent to the EPK robot controller. The value of the override factor is shown both on the Safety Manager graphical user interface and on the shell where the EPK robot controller emulator is running. The override factor decreases until the worker reaches the protective area. If he oversteps this bound, a signal of stop is sent to the EPK robot controller, and it is shown always both on the Safety Manager graphical user interface and on the shell where the EPK robot controller emulator is running. If the worker comes back outside the protective area, the Safety Manager restarts giving the permission of work and setting the right override factor. Now, let's suppose that you want to allow the worker to approach the robot for collaboration tasks. From the P4C central controller emulator, it is possible to change the supervised areas and set, for example, the user case 3. The shape of the area is changed and an available corridor is shown. Now the worker can reach the robot to exploit his tasks. Within the warning areas, the override factor is always transmitted and the velocity is always reduced proportionally to the distance between robot and human. If the worker oversteps the corridor and enters in the protective area, the robot is stopped. When the worker's task is completed, he comes back to the initial position, and the area can be restored. Thank you to everybody for the attention.
For any further information, please visit PiSA Integrated Project website or EICASLab.com website.